it's gonna be recorded via the YouTube stream. If you, Maurice, are still okay with that, we are streaming the talk as well. Okay. So then Julio, whenever you want, if you want, you can start the YouTube stream.
I just did. So
okay. Then. Yeah. Okay. Then starting now, this is being recorded, and well, I don't know, Jose, if you want to do the introductions, or I can go ahead.
Well, I'm happy to introduce Maurice. Maurice Fallon is actually a guy with a stellar academic record. He got his PhD from the University of Cambridge. Then he went for a postdoc at MIT, and now he is a Royal Society University Fellow at the University of Oxford, and he leads a dynamic robot system group within the Robotics Institute at Oxford. We are extremely pleased that Maurice was able to accept our invitation. He's going to talk about, as you know, from the title, legged robot in caves and slightly scary places, and especially difficult places for robots to deal with. So, Maurice, thank you again for accepting our invitation, and you can start whenever you're ready.
Okay, thanks very much, Jose. Thanks very much for the invitation. I'll do the usual and turn on PowerPoint. If people can't hear me, or if my video isn't coming through, then
we can hear you fine so far.
Okay, great. Well, good afternoon or good morning where I am for a little bit longer. Thanks very much, Jose, for the introduction. And I'm going to talk about the work we've been doing for perception and navigation for legged robots, and with particular emphasis in the last year or so on legged systems in underground environments. My background is, as Jose mentioned, involved, I got into robotics in particular when I did a postdoc in MIT, and I was working with John Leonard, who is, along with Jose, one of the key drivers forward of the research area of simultaneous localization and mapping. Worked on two projects that you can see here to do long-term multi-floor mapping of a 9-floor building that we had in MIT, and also this handheld body-mounted system. And actually, both of those projects used a software library developed in Zaragoza by Juan Domingo Tardos's student. And through that, I worked with actually Cesar Cadana, who was one of Jose's students at that time. But I took a sort of slightly left field direction and got involved in a large-scale robotics competition called the DARPA Robotics Challenge, which you might be familiar with. It ran until about 5 years ago, and it involved a slightly clunky older version of the Atlas robot from Boston Dynamics, doing a variety of manipulation and locomotion tasks. And I had the role of leading on the perception side of things, and in large part that involved focusing on state estimation and local situational awareness and mapping for the robot to do these tasks. And quite a number of our team have now gone on to work on the actual Atlas team in Boston Dynamics. One of the projects I was involved in at that time that I was most interested in was trying to couple perception into the locomotion system. So here you can see a system in which we have an onboard state estimator, which I'll talk about legged robot state estimation in more detail later. But effectively, we have a motion estimator that uses the robot's legs, an IMU or fiber optic gyroscope in the robot's pelvis, and then it's combining all of those measurements together to get the position of where the robot is that you see in the field of view. And then on top of that, for this particular work, we were fusing together the stereo images from the robot's stereo camera. You can see it on the left-hand side. It was actually a passive stereo camera mounted in the robot's head, which was actually quite a significant challenge. And then in doing so, able to build these reconstructions in front of the robot's feet to do receding horizon footstep planning. This was kind of one of the only major perception in the loop locomotion systems that was developed in the competition. And as you can see here, at interactive rates was enabling the robot to replan and then to execute the motion that was indicated in the video. So when I finished working on that as part of my as a research scientist or postdoc, I moved to Oxford to set up my own independent research group, and we focused on quadrupeds. So 4 legs is better than 2 is a kind of a famous phrase from a book called Animal Farm. But effectively, quadruped platforms are much more amenable to field usage and for things like exploration or inspection tasks. And you're probably very familiar with quadruped platforms like Spot and the animal in the middle that we work with. So we're working on research tasks to do with that. So building local situational awareness using visual inertial navigation and multi-sensor fusion, and also doing work on dynamic locomotion and motion planning. And I share this group with Yanis Savutis, who illustrated here on the right-hand side in orange. So we have quite a significant size group, but it's quite a challenge to do research on these platforms. But they are, I feel, kind of slimmed down in terms of mass, but in terms of sensing, they very much match the multi-camera, multi-lidar capability that you have in a self-driving car, for example. So illustrated in with these arrows are all of the different cameras that are on board the platform that we're working with as part of the DARPA Subterranean Challenge. That's a different challenge, a bit of a sucker for large-scale competitions, but this one particularly fitted my interests. So you can see here, starting from the top, if you can see my mouse, I'll just put it into pointer mode. So you can see here, actually I'll start at the bottom. So you have the robot's legs. They have joint encoders, so that measure the angle of each joint. They also have series elastic actuators. So these are springs that are within the joint that allow that through the deflection give you a measure of the level of force that the robot is applying. We have an IMU inside the robot's torso. We also have, and that's key for knowing the orientation of the robot relative to gravity. We have depth cameras. There's 2 on either side. We originally had 4, but we're removing some of those to incorporate this LiDAR at the front for mapping effectively the ground where the robot's about to step, but also the general area in front for an exploration focus. We've a Velodyne LiDAR here at the top, so you can see it's a typical automotive grade LiDAR that's repurposed for doing mapping and local environment positioning. And then at the top, this is specific to the competition, is omnidirectional cameras. So these are fisheye cameras, and I say omnidirectional, I mean they're pointing in all directions, and that's part of the competition for detecting objects. And I'll come to the competition in a second. But first, I'm going to talk a little bit about some of the controls work we do. I won't talk about it very much. Most of my talk is going to be about the perception and navigation aspects. We also do work on controls, primarily led by my colleague Yanis. This is one of the projects that we've been working on to do trajectory optimization for walking robots. So to think about a walking robot, how does it locomote? Well, one way of abstracting it is to think about the 4 points of contact of its feet, and to think about those as effectively the thrusters on a space rocket, for example. And every time a foot comes into contact with the ground, it has the opportunity to express a force, and in doing so can cause the momentum of the robot to change. So we can move the robot forward according to how much force we're applying, as long as we apply that within the constraints of contact. So contact is a major part of locomoting robots, and illustrated here by these red cones that are visible. That's a friction cone. It's a representation of the perpendicular angle that the force needs to be applied upon to the ground so as to avoid slipping, so that we can push without slipping. And also other constraints that restrict the motion are the dynamics of the system. So the mass distribution of each of the links in the legs as well as the torso, and also the kinematic limits. So that's the capacity of the robot's feet to move from one place to another or to hold up certain configurations. And in this particular work, that's simplified to this blue box. So this work on trajectory optimization formulates these constraints as an optimization problem, and that's what's illustrated here on the right-hand side. So, for example, for the left foot moving, it can apply a certain force profile over time. So this is in the order of a second of time. You can see the force in the z-axis, so that's the downward force, which is either 0 over the course of this part here, or then rises up above that, and it's limited by effectively a spline constraint. So initially there's 0 force because the foot is in air, and then forces are high until when it comes into contact, until again it goes out of contact, while the foot position conversely can move when there's no force and must stay stationary when there is force. And effectively this formulates a constrained optimization problem, which we then solve with nonlinear optimizers. We use a package called IPOpt. And I'll just mouse this. So this is to show some of the work that we've done on computing dynamic trajectories given these set of constraints. So it's work that we've just ported over to this newer version of the Animal robot. So the black robot that I show is kind of an initial prototype by a company called Anibotics from Zurich, and this platform here is a newer version developed by Anibotics called Animal C version C, and they're effectively the second competitor to Boston Dynamics in the development of legged robots. But the key advantage for us when using this platform is that we have access to the software API to actually command at 200 or 400 hertz the robot, while with Boston Dynamics, what's available to both industrial users and the academic community is just access on a high level to be able to tell the robot to go at a certain velocity of its torso. But here we're computing these trajectories for the robot to walk over pretty significant obstacles for its height, and then executing them while replanning based off of the perception. Another line of work, it's not led by me, but it's led by my colleague Yanis, and I wanted to just mention in passing, is the use of reinforcement learning to learn locomotion gaits based off of offline simulated environments. So on the first portion of this video, you could see randomized terrains that were being generated, and then we give the robot a simulated sensor of the terrain, and then we're generating reward functions to encourage kind of stable, reliable gait. Now this bit is just showing that if you provide suitable reward functions, then you can generate things that are more like walking gaits. And then when after training, what you see here is that with an accurate model of the robot, of the terrain underneath the robot, so this is a common representation that we'll keep coming back to, is this elevation reconstruction underneath the robot. It's based off of depth cameras, such as the Intel RealSense, pointing at the robot's feet, and effectively the reinforcement learning algorithm gives us a mapping between the observed terrain and footstep parameters to optimize a locomotion walking controller that then closes the loop for locomotion. So moving on to the core of my talk, I'm going to talk about multi-sensor odometry and mapping. And I'm going to frame it by the DARPA Robotics Challenge, DARPA Subterranean Challenge. So it's a multi-year competition in which teams of robots, you can actually choose as many robots as you'd like to deploy, but you've only one hour in which to deploy them, to explore unknown environments. So on the right-hand side, you can see a facility in Washington State in the US, where in February of last year, just before the first COVID lockdowns, the teams gathered to explore a a few of the floors underneath one of the cooling towers, and you can see the characteristic shape of the cooling towers here. So that effectively the robots were given 1 hour to explore the facility. It started at a gate like this, and you can see these tags that were used effectively to infer the starting point using cameras, and then thereafter the goal was to build very large-scale, accurate maps of the environment, and within that environment to locate objects of interest. So it was a giant treasure hunt. So the objects of interest were backpacks, mannequins that could be detected using autonomous computer vision, or actually reported back to an operator. So you can see here there was actually one operator. All of the other members of the team could only communicate orally with the operator, and then the operator would deploy each of the robots down the starting gate as illustrated in this video, and thereafter the robot either could communicate through its own onboard wireless network back to the operator, or would have to operate entirely autonomously. And the idea of the competition was to encourage the development of highly autonomous systems, but not actually requiring absolute autonomy, which is typically a very complex design requirement when you're working to operate in very unknown environments like this. So here you can actually see the robots actually passing one of the other robots, the drone that our team had deployed earlier in the competition, as it makes its way down the tunnel. And a little bit further down the tunnel, you can start to see some of the challenges. So you can see muddy ground with puddles of water, which are particularly challenging because if you're using a LiDAR or a depth camera to scan the ground, then these show up as blank holes. And then as it goes up the corridor, you can see one of the other robots that had fallen in that stage of the competition. So you should keep an eye out for a special issue on in the new rebooted Journal of Field Robotics that should appear in the summer, that will describe the progress of all the teams competing in this competition. And this is the team that we're involved in. Came in as a junior member of the team after the competition had started, and it's led by Professor Costas Alexis, who's just after leaving the University of Nevada to go to a university in Trondheim in Norway. And also there's a heavy contribution from ETH Zurich, who we collaborate with on the quadruped robots, as well as the ASL team from Roland Ziegert. So that's Marco Hutter and Roland Ziegert. And our focus is on aerial and legged systems. And I'm going to focus on the legged system. So one of the so I think this competition has actually demonstrated the growing maturity of both of autonomous mobile robots, but also legged systems. The last phase of the competition was actually won by a team from JPL called CoStar, deploying a couple of spot robots that were able to autonomously climb up and down staircases during the competition. But it's not the only type of platform. On the bottom left here, on bottom right here, you can see a platform from the team from CMU called Explorer. But the key comparable characteristic, as I mentioned previously, is the need for omnidirectional sensing in all directions. So depth cameras and LiDAR pointing in all directions, both around the robot's legs and underneath its belly, as you can see here, but also out in front to be able to perceive where free space is. And that's made possible by the miniaturization of multiple i7 CPUs, and also one of the technologies that I won't talk about that is a significant part of this competition is the ability to deploy communications within the facility. So if you take one of these mobile robots that are exploring an unknown facility, then the first time it would turn around a wall made up of concrete, then your communications network would fall. So a significant kind of engineering challenge has been to develop deployable wireless networks that, as you can see here, this one is dropped from the robot's the belly of the animal, and that can then be used to create a kind of mesh network that allows the operator to kind of communicate deep into the facility. And obviously, another aspect is mobility, and as I mentioned, I won't focus so much upon that, but the spot robots pretty impressive at this regard. What I will focus on for the rest of the talk is on the 3D mapping systems that we've been developing. The given the multitude of different environments that we're being expected to operate in, including the addition of artificial smoke, which can have a really negative effect on LiDAR, for example. These are 4 different types of odometry that we'd like to be able to take advantage of in our platform. So you can see, as I mentioned, forward-facing cameras, the LiDAR, the legged contribution, and thermal odometry, which I won't talk about very much today. And I'll start with leg odometry, with a background in the DARPA, the humanoid challenge that I mentioned previously. I started working on quadruped systems, and what you can see here is a quadruped from a group in the Italian Institute of Technology in Genoa, which develops this quadruped robot called HiQ. And one of the challenges that you can see from it locomoting are that when its feet press against the ground, it causes quite an impact, and that can have a significant effect on leg odometry. So leg odometry is a process by which, when a robot makes a firm foothold in the ground, as you can see here, we can use the knowledge that a particular foot is being classified as being in contact to create a constraint and to infer the forward velocity. So effectively, you have a lever arm where you assume a particular foot is in contact with the ground, and as the rest of the robot moves forward, you can infer its relative motion from each one of those contact points. However, there's quite a significant filtering challenge in doing so, because as each foot comes into contact, you get these spurious velocity spikes, which can. Sorry, is there somebody with their microphone on in the background? So you can see these very spurious velocity spikes, which makes actually incorporation of this within a control system quite challenging. But over the course of that project, we developed an extended Kalman filter based quadruped state estimator. So an extended Kalman filter is incrementally carrying out IMU based propagation. So either with this fiber optic gyro from a company called KVH on the bottom left. So that's effectively measuring the movement of light around a sphere inside of the fiber optic gyro, and being able to use that to infer very accurately rotation. Or more commonly these days, we focus on MEMS grade or lower cost electronic based IMU sensors. And within an EKF approach, we're predicting the state and then correcting it with the leg kinematics. Onto that work, we incorporated both vision and LiDAR. But what we wanted to do in the work that we've done in the last 3 to 4 years is to instead look at fusing the leg kinematics that I mentioned on the left-hand side, which is reliable. It gives you a low drift rate, and it's very, very low latency, because effectively at 400 hertz you get each update of your IMU sensor and your robot's leg kinematics, and to incorporate that with vision going forward. So visual inertial odometry, as you would have heard from talks from Davide Scaramuzza and Stefan Lutniger during this series, is an increasingly mature field in which measurements from an IMU and either a mono or a stereoscopic camera are fused together to constrain the motion, usually on a drone platform. But because of the dynamic effects of a legged system, so aggressively walking and trotting on ground, its feet slipping, for example, and the necessity to do very high frequency reconstruction of the terrain around the robot, visual inertial odometry has great promise to improve local situational awareness. So what we've been doing for the last 3 years is developing a methodology to use visual inertial navigation systems within a legged platform. We call this VINs. And as I mentioned, one of the key motivations is that on these robots going forward, we're likely to see multiple depth cameras, such as the RealSense, which also has an IMU. This is the Intel RealSense D435i, and it has an IMU inside. So it's a fully usable sensor for visual inertial navigation. And I'm going to frame visual inertial legged navigation within the same framework as the general problem of visual inertial navigation for drones. So we're interested in estimating the state vector of the robot, its orientation and its position, its linear velocities and biases, where the biases are effectively due to poor performance of the underlying sensors that are providing us with IMU measurements. So they are subject to characteristic drift sometimes. So you have your gyroscope and accelerometer, but in addition, for the quadruped system, for the work that we've done so far, we have this continuous stream of motion estimate from the leg kinematics, but we don't actually have a very good characteristic for the materials that the robot is stepping in. If it's concrete, if it's mud, for example, it's soft. But we're required, or we're reliant on understanding the nature of contact to be able to precisely estimate the motion using leg kinematics. So in the work that incorporates vision, what we'd like to do is to take effectively the remaining error and noise that comes from the leg kinematics and use that to estimate a kind of separate bias state. So these are biases that give us an observation of the non-Gaussianity of the leg kinematics. So if, for example, the robot's slipping or sinking into ground like gravel, then we can actually passively infer that bias within our estimator. And if you're familiar with this representation, this is called a factor graph. It effectively formulates all of the constraints of the robot's odometry and illustrates the relationship between them. So if you look only at the upper half of this figure, you can see a series of IMU constraints between consecutive states of the robot. The x0 being the states of the robot. You can see on the very top in green, these are visual constraints to features that have been observed in the environment. So points and corners in the images, while at the bottom is these velocity bias constraints that I mentioned. So the red elements on the bottom are contributions from the robot's leg kinematics. So these, and otherwise, without the red elements, the approach falls back to a more typical visual inertial navigation formulation. So given that, we can formulate a least squares optimization problem with these terms, and then our approach typically formulates this as a least squares optimization problem. We use robust kernels and then can solve that using GTSAM. So just a note on how we incorporate the kinematics. So I mentioned previously that when a foot is in contact with the ground, we can use the inferred contact of the foot to give us a measurement of the velocity of the robot's base link. All of our estimation is typically done either in the camera frame or in the base link of the robot. They're rigidly attached to each other in the robot. And then I won't go into this in great detail because it's quite specific, but effectively we're able to estimate this evolving bias term on the velocity of the base due to the non-Gaussianity of the kinematics. And this bias is approximately constant for a particular gait or terrain type, but it allows us to effectively retain this underlying assumption of the Gaussianity of all of the measurements that are going into our least squares optimization problem. Otherwise, the front end of our system follows a typical approach for state-of-the-art visual inertial navigation systems. We incorporate, because the robot is operating close to the ground, we can use stereo factors. So these are the blue features that are being tracked here are being triangulated from a stereoscopic camera that's pointing slightly towards the ground, with a KLT feature tracker to retain them over time. And this this provides us with visual feature constraints for the factor graph that I've described before. I'll give you an indication of how this works. So you can see here the green line that you see in this plot is the ground truth from a motion capture system. So you can see here there's a reflective prism that's attached to the top of the robot to allow us to be able to track the position of the robot in an outdoor environment, in a realistic test environment. And you can see this green line, which basically gives us the ground truth that we're targeting. In the bottom left, you can see blue dots, which correspond to the visual features that are being tracked, and in yellow are the visual features projected into 3D. And you can get a feel here from the fidelity of the fusion of these two different sources. And we're doing that despite the fact that the robot's being kind of pushed around and being walked over various types of rubble. And here's another example. I'll jump to here. This is an industrial test facility where I'll pause it at this point here. We have the leg kinematics of the robot, as I mentioned, and the constraints from the vision. In this particular circumstance, there's standing water in this test facility, and that's causing reflections from the sky. And in blue, you can see a significant number of false features due to water reflection. And because we have this joint optimization between the kinematics and the visual features, we can disallow the visual features that are incorrectly or inconsistently being tracked. This would be a failure mode for purely visual inertial navigation. You'd have many features that were inconsistent, which could cause your estimation system to diverge. So it's an indication of the multimodal robustness that we're targeting for, so that we can achieve, so we can overcome some of these performance challenges. That's just an illustration of the algorithm performance. This is, I think, 400 meters of walking, and there's in the order of 5 to 10 meters of error. One of the reasons in the DARPA competition why accurate mapping is so important is because when you detect the artifacts, the treasure that I was talking about, you need to report it back to a base station for DARPA to give you points, and you have to be within 5 meters even after operating for 1 hour. Okay, so at the start of this year, we were actually quite fortunate to be transitioning slightly to look at a different combination of multi-sensor fusion. We started looking at incorporating LiDAR more significantly within our high frequency estimation. So previously we'd been doing LiDAR odometry at much lower frequencies downstream from our visual odometry, but we wanted to work towards incorporating them jointly within the estimator for a couple of reasons. So this is an illustration of a payload that we built that combined together the navigation camera that I talked about, but also a newer model of LiDAR made by a company called Ouster, which is has a very large number of beams per unit price. It's probably not as accurate as Velodyne, but we've been interested in using it because it allows us to do things like transforming LiDAR points into camera images, and that allows us to, for example, be less dependent on stereo calibration, and also gives us the capacity to fuse different constraints from these different modalities. One of the key advantages of both of these sensors is that they can be synchronized to a PC inside the box passively without hardware synchronization. So we wanted to make this payload and the fusion of both LiDAR, IMU, and vision constraints within a single modular payload, a sort of a focus of our work in the last year. And we just happened to have this platform put together in February or January last year, and it's kind of give us an opportunity to do a lot of work that was easier to do without a robot platform during the lockdowns that we've had here in the UK. So we adapted the work that we were doing with the vision and legged system to incorporate low-level constraints from the LiDAR. There's a very common LiDAR odometry package called LOAM, which is probably the best performing laser odometry system. And what we wanted to contribute that might go beyond the state of the art was to incorporate primitives that could be tracked over a long period of time. So while LOAM is effectively the state of the art of laser odometry, there are a few degenerate modes where the algorithm fails, in particular long corridors. And we wanted to be able to jointly fuse together all of these estimators so as to be able to get kind of the best of both worlds. So what you see here in red are edges that have been detected from the LiDAR. So that might be, for example, in the LiDAR, you might detect this edge here to do with like the observation of a door jamb, for example, or a plane. So this would be a flat plane or plane patch that you might detect in the environment. And by fusing all of these together into a single estimation problem, then you can naturally trade off all of the constraints. So the factor graph that you saw before, we've changed it slightly. All of the elements on the bottom of this visualization pertain to LiDAR, so LiDAR plane constraints and LiDAR edge constraints, again solved as a least squares optimization problem. But before we get to that, to get to results about this type of fusion, it's important to reflect on the fact that LiDAR is not a globally shuttered sensor. So on the right-hand side is taken from Wikipedia, is an illustration of the scanning process of a LiDAR sensor. There's a mirror that's rotating continuously. It typically does 10 revolutions per second on automotive-grade LiDARs, such that the amount of time taken to accumulate a scan is 1/10 of a second, evenly spaced across the scan. And if you don't account for that, then you'll get your raw scans will be projected into point clouds, illustrated here on the left-hand side. So this is at the center here. You see an axis that's rotating around, and that axis is being estimated from a vision system. So it's not actually part of the estimation here, but what you see in red are the projection of the LiDAR points subject to that frame. And you can see that there is a significant amount of distortion and shearing of the point clouds due to the motion of the sensor. While if we were to account for the incremental motion over the course of that 1/10 of a second, we can do much better, as you can see on the right hand side. It's the same data set. The motion of both markers are due to a vision system, while the left is the raw point cloud and the right is a motion corrected for point cloud. So this is in a room of a few meters square. So this is the case for correctly undistorting LiDAR every single scan and every single beam. The other major challenge is to do the least squares estimation that I talked about. We need to be able to incorporate constraints from all of the different sensors in a single coherent time frame. And as you can see here, we have sensors that are coming in at very different frequencies. So we have an IMU at 100 hertz, for example, or maybe even higher. We have a camera at maybe 30 hertz. And we have the LiDAR that what's illustrated here is intended to indicate continuous accumulation of a single scan. Now, our approach is to use the machinery of IMU pre-integration. So this is a piece of work that effectively bundles together the IMU measurements so that it integrates effectively 3 IMU measurements per camera. And then we can use that initial guess from the IMU motion to do the undistortion that you mentioned previously, and then to create constraints from the plane patches to estimate the motion. So there's a kind of a bootstrapping effect in which we need to continuously estimate the motion of the platform using IMU to then project the LiDAR correctly, to then constrain the motion of the IMU for the next iteration. So it's a tightly coupled estimation problem. And the reason why despite the complication of tightly coupling these things, the reason why we feel this is a significant improvement is that we can do away with these blocks that are indicated in red here. So these are 3 of the systems that have been developed as part of the DARPA challenge to do multi-sensor odometry and to overcome the different limitations of the different sensor modalities. But effectively, the red boxes are basically complicated if statements. So given multiple odometry sources, how do we multiplex or choose between them to give an input into a mapping system that's from the team from JPL? This is a part of our own current system, given 4 modalities here. How do we check the health of each of the different modalities? So if the LiDAR is working, then, or if the LiDAR is not working, then we fall back to maybe the vision system. And that's what's indicated here. If the visual system, or if the laser scan matching is not working, then this illustrates using the visual inertial odometry directly. So our approach with this factor graph is fusing all of these partial constraints. We might only have a small number of visual features, a small number of planar patches from the LiDAR, but whatever is available in whatever environment can be fused together with our approach without needing to be hand crafted decision switching mechanisms. So we happened to introduce the validation of this work, and we developed a large-scale data set for multi-sensor odometry and mapping. So we have the RealSense vision and IMU sensor. We have the ouster sensor at the top, and we mounted it on a portable payload, and we're able to achieve accurate synchronization by aligning the IMUs of the two different devices. And we collected this large-scale data set in one of these colleges we have in Oxford. It's effectively a combination of a built environment, as you can see in the picture there, and some natural environment. And we took some large-scale data sets of a couple of different types of speeds of walking, and levels of dynamic movement of the sensor. And we've developed this data set that's now been downloaded by over 250 users, and it's also already been used in a number of different papers that are appearing at ICRA this year. What's particularly valuable from the sensor, from the data set, is that it comes with a very accurate ground truth. So we use this stationary tripod-based Leica scanner to very carefully build a large-scale 3D model of the entire facility, and then we were able to post-process the model to be able to generate ground truth for the odometry of the mapping system. And if Jose is listening, I'm absolutely sure he's very familiar with the grounds of this college, because this data set kind of alludes to an older data set that was developed by my colleague Paul Newman maybe a decade ago now. And just to illustrate a little bit more about the relevance of the data set, on the right hand side here, I'll play it back. You can see in blue, hopefully it's coming through, in light greenish blue is the prior map. And what we did so as to generate reliable ground truth is post-processing the sensor odometry and then aligning it with the prior map to give inferred ground truth. And you can see here, despite the aggressive motions of the sensor towards the end of the data set here, we're still able to have very accurate projection of the LiDAR data, so as to be able to give very important valid evaluation and quantitative results for our algorithms. And here's another example of one of the other data sets where we're very aggressively rotating and shaking the device so as to be able to do things like improve the undistortion correction that I talked about in the previous slides. Okay, so here's an illustration of some of the experimental results that we had from that work. There's an illustration with the quadruped of the environment where we're interested in working. The robot's carrying all its own lighting source above it. There are some parts of the scene that are very long corridors where, as you can see here, it's kind of about a 100-meter long, or maybe a 50-meter long corridor, where there's few planar constraints, and few of the LiDAR beams actually make contact with the ground. And this illustrates the algorithm operating in this unknown environment, where again, the yellow features yellow points correspond to visual features, red lines correspond to edges detected in the LiDAR, and green patches correspond to locally flat regions. You can get a feel there for this arc from the cooling tower. Okay, and I'll move along to talk about a couple of other projects that we're working on. So we wrapped around this work a large-scale SLAM system. So this is a post-graph SLAM system, again using factor graph-based optimization and a combination of geometric and visual loop closure. And you can see here it functioning on the New College data set, where each green flash corresponds to a LiDAR loop closure detection and trajectory optimization of the entire SLAM trajectory. And these kind of capabilities effectively of locally building very accurate maps, and then being able to, where globally there is inconsistency, to be able to correct for that odometry drift, is the basis for the capacity to have the robot to explore in unknown environments. Now, I don't have very much time to talk about this, and it doesn't necessarily fit directly within the work that that we've been doing underground, but it's an interesting adaptation of our SLAM system to do large-scale volumetric reconstruction. It's in collaboration with Stefan Lutniger's group in Imperial College, and it's just been accepted for ICRA and RAL this year. One of the challenges with being able to do long-range motion or exploration planning is the ability to be able to create accurate reconstructions so as to be able to do free space planning. So imagine the scenario where your robot you want your robot to explore through this tunnel here. Previous approaches, for example, a library called Octomap, is unable to fuse together both highly detailed volumetric, so voxel-based reconstructions at long ranges at high frequencies. We'd like to be able to, when entering an unknown environment, to be able to quickly build a 3D reconstruction of the surfaces of the environment, to be able to do things like identify where to go to next to further explore the environment. So our work with Stefan's group in an Imperial has extended their approach called Super 8, which maintains multiple different resolution reconstructions at different levels of detail. So you can see here at low detail we see a reconstruction in gray, and in higher detail at shorter range we've got more accurate reconstructions. So we're able to get kind of nice trade-off between detail of reconstruction, as you can see in green. We've got some very pretty reconstructions of the detail against being able to reconstruct from quite a long distance away. And we've been working to adapt this to be able to fit within an Atlas framework, which is a kind of a sub-mapping framework in which, as illustrated by the color here, parts of this volumetric reconstruction, this is not point clouds, this is actually a representation that supports knowledge of the occupied and free space. We're able to scale the volumetric reconstruction by having submaps and then deforming them according to the SLAM graph that's underlying. And the reason why this is interesting is that for some of our most dynamic platforms, this allows us to create a volumetric reconstruction. So this is one of our test experiments in an underground facility. And you can see here the system closing loops and deforming the map. And then eventually at the end, using this occupancy map reconstruction, we can then optimally find routes from A to B, despite the complexity of this kind of facility. Okay, a few more things I'd like. One more thing that I'd like to talk about. I didn't really very much talk about how we do exploration in the underground facilities. In large part, that's because this has been within the DARPA challenge. That work has primarily been led by my colleague Costas Alexis in the DARPA team. But our own work in this space, just to give you an indication about how the SLAM system can be crucial to the deployment of an exploring robot. I'll talk a little bit about work that we've done to deploy the Animal in an underground mine that we have close to Oxford. So we'll typically talk about a 2.5D representation built from the robot's depth cameras and also from LiDARs. It stretches out to about 5 meters around the robot. And the robot effectively carries out an iterative process of detecting frontiers on this elevation map, as indicated here by these yellow and red dots, and then choosing one of those and then planning a route, typically using RRT or RRT star, and then iteratively expanding and exploring the map subject to there being available space. Primarily, we've been carrying out experimental work in this large underground mine that you can see on the right-hand side. It was actually built as a bunker as a safe place for the British royal family during World War II. So it was, or during the Cold War actually. There's a direct rail line from the west of London to this facility. And gradually over the course of the Cold War, eventually it became decommissioned, in large part because it was built in limestone, which was permeable. So the water eventually, if it was irradiated through a hypothetical nuclear attack during the Cold War, would actually have been unsafe, but it's a large scale, approximately the size of 100 football fields, the space that we use for exploring. As you can see, the facility is entirely unlit, so our animal is fit out with artificial camera or artificial lighting, and you can see here iterative phases of the robot, planning and exploring. So you can see in the green arrows are the markers which indicate the next route that the robot selected. You can see some dynamics. That's actually people that are following the robot behind, but they're being quickly cleared out by the lidar that's continually reconstructing the free space. And this is a kind of a view into how our exploring robot can expand and explore underground facilities while using the pose graph effectively as a highway. So it's able to use the graph in green to indicate when it's finished exploring a certain area, and then to return to maybe mop up any junctions or any areas that were unobserved in earlier parts of the map. And so yeah, we do work on radiation mapping on top of this. I don't really have the time to talk into it. So this is an illustration of a radiation map that could be built, for example, by a robot exploring or being used in first response. I have some work on upcoming work on multi-camera odometry, using learning within legged kinematics, and also expanding the work to multiple floors. So this is a large-scale SLAM map that we've built with a copy of the Spot robot, exploring on multiple floors of our own facility. But I think I'll finish at this stage, and I'm happy to take questions at this stage if you're still with me.
Thank you, Maurice. That's really amazing work. I think that the way in which we do the questions is, if somebody wants to ask a question, please write first in the chat so that we can give turns.
Okay.
So I can check that.
Jose, I'm sure you've used many papers with Paul Newman's original New College dataset. Yes.
Actually, we did a prior dataset at Oxford, but it was in Andrew Davison's college. I can't remember the name.
Oh, that goes back quite a ways then.
Yes.
Yep.
Close to the new engineering building.
Okay, Keble College maybe.
Keble College, yes.
Okay.
Yep, absolutely.
There's a few colleges that are most amenable where there's flat ground for the most part.
Yes. Yeah. So that's prehistoric data sets.
I'll have to dig that one out and find out.
That was only with a monocular camera, with a webcam actually, and nothing more. So it was very, very primitive. I think David wants to ask a question. David, go ahead.
Yeah, I can't speak right now, so if you could read the answer for me, please, Jose.
You wanted to read the question, actually?
Yeah, please. Yeah, it would be better.
Yeah, I will do that. So about the contact point of leg robots, are there any lines of research or ideas towards applying active perception to test, for example, stability of the terrain? Would they be useful, or is it not so necessary after the results reported by Animal or Boston Dynamics?
I mean, we have, I don't know if it's in my backup slides, we have a paper. We had a paper recently on. I'm just trying to see if there's anything in my backup slides pointing to this, because it probably has drifted out. So we have had work in a project, an EU project called Thing, which kind of started me doing work in the underground environment. I'm just looking through the backup slides here. I don't see the work there anymore. Using effectively making experimental footsteps, so probing with a foot to determine whether a particular foothold is safe and reliable, and then using it actually as a sensor probe, so scratching on the ground to determine material properties. And we did some work with in collaboration with ETH on using it actually in a sewer to scratch concrete, where we install IMUs on the foot to be able to determine the material properties I think we used an SVM to classify whether it was smooth or whether it was gratey. So, for example, where the concrete was still in good condition. There tends to be a preference to use less engaged sensing on the robot itself. None of these robots use sensors in the feet to detect contact. So sensing the contact of a foot on the ground is inferred usually using force sensors in the shoulders, in the shoulders or in the knees, rather than directly at the feet, because typically as time goes to infinity, when you have a foot that's striking or hitting the ground, then eventually they will break. Quadrupeds usually use force sensors in the robot's ankles, but humanoids use force sensors in the robot's ankles, but for quadrupeds, especially to keep the mass low, so the more mass you put in the feet, the more you're working against it when you're walking. So it's actually a very deprived sensing scenario when the robot's walking, to be able to infer what's actually going on underneath its feet. So which kind of tends towards an indication why reactive locomotion is important.
Yeah, I see. So the second part of the question was, in the same way, are there active perception strategies applied in order to enhance vision in the subterranean challenge using suboptimal trajectories to improve perception?
I mean, I could talk for quite some time about the challenges that we have underground. In that, I would say that most of the approaches that you can see, I think you're still seeing my slides. So the output of nearly all of the teams competing in the competition at this stage has been accurate reconstruction of the facility that you can see here. So robots operating for an hour, usually a duty cycle where they're standing still for half of the time but walking for half of the time. And because of the variable lighting conditions, there's been a predominance of LiDAR approaches. Now that we do have headlights on the robot, so we are doing visual inertial navigation, but typically the lowest common denominator on the systems has been LiDAR-based approaches, and I don't think that any team is particularly doing motion planning to favor vision. It's more that both your LiDAR and your vision systems just have to work. So if you walk through a very narrow corridor and all your visual features suddenly change because your field of view is entirely different, then you need to have mobility, or you need to have reliability with other sensor payloads. So in that kind of scenario where you have a very narrow constriction, you need for the quadruped system, leg odometry, or for the wheel system, obviously wheel odometry. So there's not really adaptation of the platform. What I mentioned in passing was that there are multi field of view cameras that you can see here. So one of the works that we're doing to mitigate failure mode is, this is only initial work. Got it. Too many backup slides, hundreds of backup slides. I just chuck everything down there when I'm making the talk. Is this robot is made up of, the robot camera payload is made up of 170 degree field of view fisheye cameras pointing in all directions. So this is kind of initial work on the forward camera is in the bottom right here, and the left, the right and left cameras are here on the left hand side. It's a bit confusing, but by having multi cameras in different directions, then we can mitigate some of the visual feature change to sort of seamlessly switch between cameras. And we can also do things where we're tracking visual features in the forward-facing cameras. Then as we move along, they get picked up on the side-facing cameras to maintain continuous feature track for extended periods of time. So I hope that answers that question.
Yep. Okay. So I also have a question actually related to the learning of walking.
Yeah.
Because I wonder, as far as I know, when you're accustomed to, for example, stepping down in stairs, and if there's a step that's slightly off, that tends to be a problem. Is that? So I wonder that maybe because we have a bias in the way we learn to use stairs that we expect all of them to be equal. So does that type of thing have any effect in the way that you generate the random terrains for learning appropriately to walk? Or so what are the issues with generating simulations and random terrains for learning to walk?
So just thought you mentioned going down, and actually that's for perceptive locomotion. Walking upwards is actually vastly easier. So when you're walking up a staircase of steps, as you might see, I might have clipped it out of the start of this video here. Let me see. You see all of the frontal facings of all of the steps, so you can see sharp edges as the robot. This is actually the full map after the full reconstruction, but yep. But if you can think of what the field of view of what the robot's seeing, and maybe it is shown in part of the video here, you can see this is the field of view of what the robot is seeing. I don't know if it actually appears on the screen here at any point, but effectively you've got a nice perpendicular view of it doesn't actually appear in the video. A perpendicular view of all of the step edges. While when you're walking downwards, you don't see clearly the steps until you're right over the top of them. So the place where the robot would like to step is as close to the near side of the step as possible, but that's effectively hidden by until the robot is over the top. So what you see here on the right hand side is the reconstruction, and compared to the reconstruction earlier in this video, the latter part of this is actually very blurred. So this was by far the hardest part of this experiment, was walking downwards. So there is a need for a little bit of learning work to actually, on the perception side, to regulate the reconstruction, so as to regularize the reconstruction, so as to sharpen reconstruction in a downward direction. It's vastly harder for a robot to perceive going downstairs for this reason. But on the reinforcement learning part, there's no particular. We haven't particularly got to the stage of adapting it specifically for downward facing directions here. Here you can see probably that we have sufficiently far enough away that the robot is able to perceive. Each of the steps are sufficiently wide enough that we are still able to perceive the boundaries between steps. And by and large, the reactivity of the robot is what's needed to kind of pick up the slack. I would say that there's some important design decisions that Boston Dynamics have made to have their system be more reliable in this scenario. They have a much wider field of view depth camera than antibiotics have, for example. So there's a kind of a relationship between the sensing and the reconstruction, as well as the motion planning that's necessary.
Sure. I guess another difference might be that actually the robot is trying to pay attention to the stairs, but specifically to decide how to move, while humans, we tend to be thinking about different things and maybe inferring what the size of the steps is, and then assuming that it's going to be like that all the way up or all the way down. Yeah, that would probably be a difference also.
Yeah, well, effectively, when walking down, we're often not looking at each step. So we have in our minds a regularized model. Like with the work that you saw in this, I mean, this is a kind of more of a standard, closer to a standardized staircase, let's say.
Right.
If we wanted to achieve the best reliability, we would start firmly or specifically detecting the edges, so as to ensure that footsteps don't come as close as this. If you want to go from 90% reliability to 99.9% reliability that the Boston Dynamics are able to achieve, you wouldn't have a robot climb up or down a staircase without it assuming that the footsteps or the staircase steps are regular and evenly spaced.
Sure. Okay, so there's a question from YouTube. How do you create the synthetic terrain for training the models? And what is how is the performance with respect to real terrains? So it's a related question.
So the simulator package that we're using here is called RISIM. It was developed by a PhD student and graduate from Marco Huder's group in RSL, and it's available in an academic license, open source, and these are effectively procedurally generated terrains that are they're kind of graded according to the degree of complexity. So there's a kind of a periodic increase in the complexity of the learning as the locomotion improves. I think that effectively kind of answers that question. And given sufficient variety in the simulated training environments, then adaptation to the real platform has been successful. I mean, we do also test in with a full kind of software in the loop validation. And then one of the things that I should mention is that what this particular reinforcement learning controller is doing is adapting an underlying whole body controller. So this is not doing full model-free reinforcement learning. This particular approach, although Sid, the primary student who led on this work, is doing kind of full end-to-end reinforcement learning in other strands of his work, this particular work actually adapts a more traditional whole body controller. So one that's doing the kind of optimization-based motion planning that I was talking about before, and it effectively is trained to detect or to choose the footsteps as well as to choose the body posture, with the kind of more traditional engineered system beneath that, balancing force and maintaining a periodic trotting gait. So this is a sort of a mixture between reinforcement learning and more traditional optimal control.
There's another question. There's more questions. So you have to tell us when you are out of time.
Okay.
So one more question from Diego is, what are the main differences, advantages, and disadvantages of using legged robots instead of drones or wheeled robots in such environments?
Okay. Well, I don't know if I have the scenario here. Most of the teams actually in this competition have been using a combination of platforms. So I don't know if they're we've been working with a company called Flyability, the team as a whole, not me personally, and their drone is enclosed in this ball. It's specifically kind of been developed for hard to reach environments where it will need, when it makes contact with, for example, a chimney, it would neither damage the chimney nor damage itself, so it can stay flying. So other teams in the competition are using similarly protected drones, but flying in tunnels is very difficult when you've got a very small payload and a 10 or 15 minute battery life. So many of the teams will be deploying, especially in the final phase of this competition, will be deploying drones directly from either their wheeled robots or quadrupeds to go up into the hard to reach spaces. So they don't necessarily have the endurance, and it's very difficult to get sufficient certainty to fly at the open space velocity. When I mean the open space, I mean drones can fly at 10 meters per second outdoors, but in a confined environment, they're kind of limited by the capacity to perceive and plan. So that's in the aerial side. I think they're primarily being used in hard to reach spaces or areas where the legged or ground platforms can't access. I kind of just mentioned it like maybe here, but the Spot robot used by JPL was the only team that was able to map 2 floors of the facility. This indicates 2 floors, but there was actually 4 floors split into an A course and a B course, and in the different runs, the Boston Dynamics Spot robot was able to explore 2 different floors of one of the facilities. So going up a full industrial staircase, and its on-ground mobility is as good as a wheel platform, but when you have obstacles on the ground, so whether it's ramps that the organizers DARPA included in the competition, or straight up staircases, then legged systems, that's the general premise of legged systems, is that they can go over these kind of obstacles. And it's interesting to see legged systems coming out near the top of the competition.
Very good. Any more questions?
I think Maurice before told us that he couldn't stay much longer. I don't know if this is maybe, I don't know, Maurice, you tell us if you can take well, I don't know if there are more questions, but maybe Maurice cannot stay longer.
Yeah. Okay, so we can leave it here. Maurice, we are really grateful that you were able to accept our invitation. You know, in normal times, we would have invited you to come here maybe for a part of the PhD jury and give us a talk, and then we would take you for tapas in the evening. So when normal times return, we hope that we will be able to fulfill that promise of treating you in that way.
Thank you very much. The closest I've got is Pamplona, so I haven't made it to Zaragoza yet. I'd love to come. Okay, so that would be excellent. When times become reasonably normal, then we will be happy to host you here. Okay, thank you, Jose. Thank you so much for giving us again. Cheers. Okay, thank you very much. Bye-bye.
Thank you. Thank you, Maurice. Bye-bye.
Bye-bye.
Thank you.